Welcome to the landing gear and brakes lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: landing gear system overview, landing gear extension and retraction, landing gear manual extension, nose wheel steering on ground, wheel braking system, auto brake system, anti-skid protection, and parking brakes. The landing gear system on the 737 NGX is made up of two main landing gear in the center fuselage and one nose landing gear in the forward fuselage. Each landing gear has a set of two wheels, and all landing gear are retractable into the aircraft's fuselage. The landing gear is designed to sustain the weight of the aircraft when it is on ground, as well as absorb the load forces when the aircraft touches down during landing. Each landing gear has a series of shock absorbers that compress when there is weight over them. If landing gear shock absorbers were rigid, they would immediately break when the aircraft touched down. They have to be able to compress sufficiently without damaging themselves or any other components around them. The 737-800's maximum landing weight is over 65 tons. All that weight must be absorbed by these shock absorbers. The landing gear is extended and retracted with the landing gear lever located in the center forward panel. The lever has three positions: up, landing gear is fully retracted and secured; off, landing gear system is free from hydraulic pressure; and down, landing gear is commanded to extend. A lever lock prevents the landing gear lever from accidentally moving to the up position on ground. Extension. When the landing gear are in the up position, they are held in place by up locks. In order to extend the landing gear, normally the pilot not flying pulls the landing gear lever and brings it to the down position. First, the landing gear doors open to allow the mechanism to come out of the fuselage. During this process, three red lights, one for each gear, located above the landing gear lever, illuminate to indicate either that the related landing gear is neither down nor locked, or that the related landing gear disagrees with the selected position in the lever. Then, hydraulic pressure from System A is used to extend the landing gear. Aerodynamic loads and gravity also reduce the demand for hydraulic pressure by aiding the extension process. Once the gear are in their down position, mechanical and hydraulic linkages hold it in a locked position in order to prevent them from collapsing upward upon touchdown. The landing gear locks must also protect the landing gear from collapsing when the aircraft lands sideways, such as during a crosswind landing. The maximum allowable demonstrated crosswind component for landing is partly a function of how much side load the landing gear can absorb during a crosswind touchdown. When the gear has come down and is fully locked in position, the red landing gear lights extinguish and three green lights illuminate. These green lights are immediately below the red gear lights and indicate that the related gear is down and locked. With this, the landing gear warning horn is also deactivated. This warning is discussed in the Caution and Warning Systems lesson. Additionally, for added redundancy, there's also an independent extra series of green lights in the aft overhead panel that provide a gear down and locked indication. This is a quick place to look just in case one of the gear lights is out. This will cross-verify the gear is in fact down. Just because a light is out doesn't mean the gear isn't down. Although these lights could be checked with the enunciates and light test, it's much easier for the flight crew to simply look up on that panel during that critical phase of flight and know if they need to discontinue the approach or if they can continue. Retraction. When the landing gear is down and locked, and the landing gear lever is moved to the up position, the landing gear begins to retract upwards. After liftoff, as soon as the pilot not flying notices a positive rate of climb and change in altitude, he informs the pilot flying by saying positive rate, who then commands the pilot not flying to raise the gear by saying gear up. At this point, when the landing gear lever is selected up, the wheels may still be rotating after being in contact with the runway. If rotating wheels were retracted into the landing gear wheel well, they may cause damage to components. For this reason, when the landing gear lever is selected up, the wheel brakes automatically stop rotation of the main gear wheels. The nose gear wheels are also suppressed with snubbers. If any of the 6 wheels have suffered damage during the takeoff roll, braking will be difficult. To prevent a damaged spinning tire from damaging any component in the wheel well, the gear stops retracting and free falls back to the down position. This gear can no longer be retracted during that flight. This is a protection in place for the critical systems that are largely housed in the gear wheel wells, like what you've seen in the hydraulics section. Now, once the landing gear have been retracted, they're held in place with uplocks, doors, and seals. That completes the retract cycle. Hydraulic pressure from System A is used to retract the main and nose landing gear. However, during retraction, the hydraulic system B may also provide pressure. A landing gear transfer valve changes the source of hydraulic pressure when the aircraft is in the air. Landing gear lever is up. One of the main landing gear is not up. Left engine high pressure compressor, N2, is less than 50%. Hydraulic system B pressure is available. Obviously, this condition is rare and would be accompanied by other warnings. But it does ensure that in the chaos of a speedily evolving takeoff sequence, that the gear will come up unless there are other limiting factors. Finally, as one last step after takeoff checklist is run, the landing gear lever is placed in the off position. This isolates all hydraulic power from the landing gear system. Landing gear manual extension. In order to provide a safe backup for hydraulic system A power loss or system failure, the landing gear system can also be extended manually. There are manual gear release handles guarded by an access door in the flight deck floor that allow for manual gear extension with the landing gear lever in any position. There are 3 manual gear extension handles, one for each landing gear. To actuate the system, the manual gear handles must be pulled aft. When this occurs, the related landing gear uplock is released, and the gear free falls to a down and locked position. Once again, the gear weight, gravity, and aerodynamic forces also aid this extension process. Manual extension of the nose and main landing gear are completely independent from the normal extension system. In case the normal extension system is jammed or inoperative, manual extension may be used. After the landing gear has been extended manually, it cannot be retracted with this same mechanism. The only way to retract it is if hydraulic system A pressure is available and the manual extension access door is closed. Landing gear lever is moved to its down position. Landing gear is then moved to its up retracted position. Nose wheel steering. The nose landing gear wheels may be used to steer the aircraft when it is on ground during taxi, takeoff, and landing, and the landing gear lever is in the down position. There are 2 ways to steer the nose wheels: with the rudder pedals or with the nose wheel steering wheel or tiller bar. The rudder pedals allow for a maximum nose wheel deflection of 7 degrees left or right. The nose wheel steering wheel allows for a maximum nose wheel deflection of 78 degrees, which is a huge difference. During taxi, the nose wheel steering wheel is used. However, during takeoff, the rudder pedals are used so that nose wheel direction is lesser and therefore the loads imposed over the nose gear during takeoff are minimized. Keep in mind that the tiller bar for the nose steering is not available in Flight Simulator and is rather connected as a function with the rudder. Therefore, tight turns available in the real aircraft will not be available in the simulator version. Nose wheel steering is normally powered by hydraulic system A. Alternate nose wheel steering is available through the hydraulic system B when the aircraft is on ground. There is a normal hydraulic fluid quantity in the B system reservoir, and the nose wheel steering switch is placed to the Alt position. The nose wheel steering switch is a two-position switch located in the left forward panel. It can be selected either normal position, where hydraulic system A powers the steering system. This position is guarded. Alt. The steering system switches to obtain power from hydraulic system B. The nose wheel steering wheel is directly linked to the steering system, unlike the rudder pedals. This means that if both pedals and the steering wheel are used at the same time, the steering wheel will have priority to control the nose wheel and will override the rudder pedal input. Wheel braking system. The 737NGX has multiple disc brakes on each of the wheels of the main and landing gear. The nose landing gear does not have any braking capabilities. The upper portion of each rudder pedal controls wheel brakes. When the top part of the pedal is pressed, the corresponding wheel brakes are actuated. For example, when either the captain or first officer's left rudder pedal top portion is pressed, the left main landing gear brakes are actuated. Similarly for the right pedal. During normal operation, braking power is supplied by hydraulic system B pressure. Hydraulic system A automatically powers the braking system when hydraulic system B output pressure becomes low or is unavailable. When this happens, the brakes operate under alternate braking. In order to provide added system redundancy, there is a way to achieve wheel braking when both hydraulic systems' pressure becomes low or unavailable. There is a system that accumulates hydraulic system B pressure in a brake accumulator so that in the event of a hydraulic failure, there is still sufficient pressure for several braking applications. The accumulator is capable of supplying 6 full braking applications or 8 full hours of parking brake application. There is an instrument in the right forward panel that provides brake accumulator pressure readings. Normal brake accumulator pressure is 3,000 psi. Maximum brake accumulator pressure is 3,500 psi. Anti-skid protection. Both hydraulic systems A and B through normal and alternate braking provide anti-skid protection against wheel skid, locked wheels, touchdown, and hydroplane protection. Under normal braking, when a skid is detected, the anti-skid system reduces the related wheel braking pressure until it is no longer skidding. Under alternate braking, when a skid is detected, the anti-skid system reduces the related pair of wheels braking pressure until it is no longer skidding. For example, when alternate braking is in place through hydraulic system A pressure and a skid is detected in one of the wheels of the left main landing gear, the anti-skid system reduces braking pressure to both wheels of the left main landing gear. When the speed difference between two wheels is 8 knots or greater, the system treats it as a skid. When the speed difference between two wheels is 25 knots or greater, the system treats it as a locked wheel. In both cases, the anti-skid protection activates. For added system reliability, anti-skid protection is also available when both hydraulic systems have failed. To notify the pilots of an anti-skid failure, as it is usually transparent and automatic, an anti-skid inoperative light in the center forward panel illuminates when a fault is detected in the anti-skid system. Auto brake system. Not only can wheel brakes be operated with the rudder pedals, but also automatically through the auto brake system. This system uses hydraulic system B pressure to provide deceleration during a rejected takeoff, or RTO, or after touchdown during landing. The auto brake system can essentially place the wheels in a near skid condition where braking is maximum. For a pilot to try this manually, he or she would make a disaster of it. This system ensures that when maximum braking is needed, it can be achieved efficiently and safely. Now for some specific examples. During rejected takeoffs, maximum deceleration is provided by this system when thrust levers are retarded to idle above 90 knots. If an RTO occurs below 90 knots, auto braking will remain armed but will not activate, and manual braking will be necessary. During landings, deceleration rates are selectable by the pilots with the auto brake selector in the center forward panel. Auto brakes only activate when both thrust levers are at the idle position, and the main wheels start to spin due to ground contact. If necessary, auto brakes may also be selected when on ground and at above 30 knots of ground speed. However, this practice is not recommended. The maximum achievable auto brake deceleration rate on a dry runway is lower than the maximum possible manual braking. Let's have a look at the controls and indications. The auto brake selector has 6 positions: RTO, off, 1, 2, 3, and max. These positions will be discussed later during flight work and ground work when we're planning our landing distances based on the turnoffs we'll need to take. The level of auto braking needed in these cases will be essential to calculate. There is also an auto brake disarm light above the auto brake selector. This light comes on when the auto brake system is switched disarmed from one or several of the following conditions. The speed brake lever is moved to a down detent. Manual braking is applied during an RTO. Thrust levers are advanced during an RTO. There is a fault in the auto brake system. This light also comes on briefly when the RTO mode is selected on ground because the system performs checks to test the auto brakes. A nice little reassurance for the crew that RTO will be available. The auto brake system is designed to bring the airplane to a complete stop unless the pilot disarms it by either switching the auto brake selector switch to the off position or moving the speed brake lever to the down detent, advancing the thrust levers, or applying manual braking. A slight tap of the brakes, for example, will disable the system. From there on out, braking is controlled by the pilot. Each auto brake position has a specific target deceleration rate, outlined in the following table. We won't go over these in detail now, as we mentioned before that we'll talk about the practical application of these numbers later when we're actually flying the aircraft. Parking brakes. The parking brake is used to retain the aircraft's position when it is stationary on ground. Hydraulic systems A or B may pressurize the parking brakes. When one hydraulic system fails, the other takes command. However, when both hydraulic systems fail, the hydraulic system B accumulated pressure in the brake accumulator pressurizes parking brakes, as we discussed earlier. To set the parking brake, both pedals must be fully depressed and the parking brake lever must be pulled. To release parking brakes, both pedals must be pushed until the parking brake lever releases. We only mention the activation of the brake here for realism purposes. As in Flight Simulator, you can simply activate the parking brake itself without pedal depression. Your controls don't actually stay depressed like the real pedals, meaning that when you let go, the brakes will be deactivated once again. The parking brake should never be set after a high-performance stop, such as after a rejected takeoff or any form of strong braking. A period of 40 to 60 minutes must be allowed for the hot brake surfaces to fully cool down before attempting to set parking brakes. The parking brake lever is located on the control stand. There is a red warning light next to the lever to alert the crew that parking brake is set. This light may also be pushed to test its functioning. All pretty simple and self-explanatory. When the parking brake is on and takeoff is attempted by advancing either thrust lever forward, a takeoff configuration warning horn alerts the pilots of this condition. This is a big duh moment for you as a pilot if you attempt to take off with the parking brake engaged. But would you believe that a takeoff has actually been performed before these warnings were standard in aircraft like the 737? All it takes is an icy runway and light weight, and it's possible to actually take off with the parking brake engaged. A bit scary to think about. Lesson summary. In this lesson, we discussed how the landing gear and braking systems work on the 737 NGX. Once again, we saw that most critical systems have splendid redundancy in place to allow control during any hydraulic power loss or other significant failures. We also discussed nose wheel steering on ground, as well as the many different protections available for wheel skid. It's important to understand the braking systems thoroughly. You don't want to find yourself hoping that your aircraft will brake in time before encountering a surprise at the end of the runway. Of course, we'll be discussing braking in much more detail later when we fly the aircraft. For now, you have a base set of knowledge to build upon. This lesson covered the following topics: landing gear system overview, landing gear extension and retraction, landing gear manual extension, nose wheel steering on ground, wheel braking system, auto brake system, anti-skid protection, and parking brakes. This was the last lesson in the controls section. Stay tuned for the next lesson to start the air systems. Until then, throttle on.